Hey everyone, welcome back. So today we're going to be solving Leetcode 2554 and this is the problem of the day for today. This is ideally not a medium level problem because the approach is fairly very simple and uh, there's no optimization also because the highest the most optimized time complexity that you can reach for this is O of n, and the space would also be O of n. But there is way to optimize a space wherein we can make space constant, but the time complexity would again increase. Let me tell you the straightaway approach, and then let me talk about an optimized approach. We wouldn't be doing the optimized space approach because it doesn't really make sense, because you'll be compromising on time and then decreasing the space, right? So we would ideally talk about the normal approach, that would give you a space complexity of O of n. Okay, so the problem states that you have an array called band, okay, and then you have n, which is the range, and then max sum is given as 6. So ideally the approach is ideally the question is asking us to give us a count of number of elements that is in the range of 1 to n, like 1 to 5, where the sum of those elements are less than 6, less than or equal to 6, and those elements are not part of this band array, right? For example, let's take the same one. Let's take the same one. So the given array is 1, 6, 5, which is band, and then n is 5, and then my target is not target, max sum is 6. Okay, max sum is 6. Okay, now here the numbers range from 1 to n, so you have 1, 2, 3, 4 and 5. Okay, here we need to find the count of all the elements, that count of maximum number of element that can reach up to the max sum and should not be present in the band array. This would be my band array here. Okay, now so let us first eliminate all the elements which are in the band array. 1, 6 is not present, and 5. Okay, what else are we left with? 2, 3 and 4. Okay, how many elements can give you a maximum of 6? It's only 2 elements, right? Either you take 2 and 3 or you take 2 and 4. These are the elements which give you a sum of 6. So then you return 2. So it's not asking you to return the elements, it's asking you to return the maximum number of integers, which means that you're returning the count, right? This is the problem statement, and let us discuss the optimal approach for now, because the constraint that's provided to us are the n ranges from I believe 1 to 10 power 4, right? So an ideal approach of n square, or brute force, or any approach of n square would ideally give us a TLE, because it would go up to n square, which means that it'll go to 10 power 8, right? So we need to think of solution in O of n complexity, right? And that is exactly what we're trying to do. Okay, so see, the thing is whenever you're given a problem, there is a trade-off between space and time, right? Ideally we would try to optimize the time as much as possible, though the space is not optimized. I'm not saying that this is in every case, but mostly, right? In this case we would try to reach an approach of O of n for both space and time. And then there is another approach where we use binary search, and then we don't have to create O of n space, and we can search it in constant time, but the time complexity would go till O of n log n. Right. I will come to that, but let me go through the approach for O of n. Okay, see, ideally what are we doing? Your n is going, the minimum value of n is 1, and the maximum value of n is 10 power 4, right? This is where your range can go up to. So if I'm applying O of n, In that case, the maximum time complexity that I can get is 10 power 4, which is good enough, right? 10 power 4 is it's good. The editor or anything or any processor will be easily able to process 10 power 4 instructions. When your loop is running 10 power 4 times, it's good enough, right? So we need to think of an approach. So we can consider the elements from 1 to n. Let's assume that this is given to be 10 power 9. In that case, we cannot consider the elements from 1 to 10 power 9, because 10 power 9 instructions, it ideally you will get a TLE. Even if you're applying O of n, you will get a TLE, because you have to process around 10 power 9 instructions, because you're iterating from 1 to n, right? Now, since it's given as the time complexity is 10 power 4, we can iterate from 1 to 10 power 4, which is good. Okay, so ideally what will I do is, I will iterate from my loop from 1 to n, 1 to 5. Okay, and what will I do? Okay, I will have a variable sum, variable count. Okay, so by this, what I'm doing is, I'm iterating from 1 to 5. Okay, I'm checking if my value, that is let's start with 1. Okay, I'm checking if my value is present in this band array. If it's present, it would not contribute to the sum, right? It would not contribute to the sum. So I need to check if 1 is present in the band array. Okay. Now, what is the time taken to search an element in an array? To search any element in the array, what do you have to do? You have to iterate through the array, right? You can't just search for the element in the array, right? If I have to search if 1 is present in this array, what do I have to do? I have to iterate through the entire array. After I have to search 5 is there in the array, I have to iterate through the entire array. Iterating through the entire array would give us a time complexity of O of n, which is ideally not, efficient, right? Because you're already iterating from 1 to n. Okay, again you're iterating through the band array, which would give you a time complexity of n squared, and also the band array dot length is given as 10 power 4 over here. So now you will get a time complexity of 10 power 4 into 10 power 4, which is 10 power 8. That would throw you a TLE, right? So now we know that we cannot iterate through the array and figure out if the element is present or not. What can we do now? Can I say that if I have some data structure, okay, which can store these elements first, okay, I can just iterate when I'm just iterating through the n, that is from 1 to n. Can I just check if this particular data structure contains 1 or not? Right. In O of 1, this is possible, right? So if I'm iterating from 1 to n, and if I find an element, I just need to check if that element is present in that data structure or not in a constant time, in O of n complexity. What kind of data structures have that? Where the search space, where the search time is O of 1 to check if the element is present or not. It's nothing but hash set, right? Set, you can store the elements, whatever elements that you have, maybe 1, 2, 3, 4, and then you can just check if 4 is present, if the set contains 4 or not in O of 1. So I can do that, right? Now we have reduced one particular iteration wherein we don't have to iterate through the band array to check for the elements. We're just gonna put the elements in the set initially. This would be the prerequisite, and after putting it in the set, what we're gonna do is we're gonna iterate from 1 to n and check if it's present in the set or not. Simple, right? So right, so from 1 to n we're iterating. I'm gonna check if 1 is present in the set or not. It is present, so I'm gonna ignore it. I'm gonna go to 2. I'm checking if 2 is present in the set or not. Okay, now I'm checking what is the value of sum. Initially sum is 0, count is 0. Is sum less than 6? Yes, it is less than 6, right? So now I can add this value to my sum. Okay, what I'm gonna do is I'm gonna make it 2. Good enough. When the sum is 2, the count of elements which is contributing has also been increased. So this also becomes 1. Okay, now I'm gonna go to the next element, 3. Is 3 present in the set or not? No, 3 is not present in this set. This is my hash set. Okay, 3 is not present in this set. Perfect. So now is 3 plus 2 less than 6? Yes, 3 plus 2 is less than 6. So I can increment my sum. This will become 5 and this count will become 2. Okay, next let's go to 4. Okay, 4. Now when I've reached 4, okay, I need to check if it's present in the hash set. It's not present in the hash set, so that's good. Now what I'll do is I'll check if my sum, this plus okay, I see. Okay, instead of adding it and then checking, why not we check and then add? What can I say? I can see that if 5 plus 4 is less than 6, then I can add it in the sum, right? So same thing, if 2 plus 3 is less than 6, which is 2 plus 3 is 5, it is less than 6, then I can add it to my sum and increment the count. Okay, now 4 is 4 plus 5 less than 6. 4 plus 5 gives you 9, that is not less than 6, right? That's not less than 6. So I have found the elements, the count of elements, which is which gives you a sum of less than max sum, and also which is not present in the band array, which is nothing but 2. So you can ask me, why not 2 and 4? Yes, of course it can be 2 and 4 also, but tell me something, doesn't matter actually, right? 2 and 3, 2 and 4, in the end you have 2 elements, right? If you take 2 and 4 also, it does not matter, because in the end you have 2 elements. So there can be only a certain number of elements which can be less than max sum, right? So it doesn't really matter because you're only focused on the count of the elements. Okay, so our approach is very simple. What we're going to be doing is we're going to be creating a hash set. That is a prerequisite. After creating the hash set, we're going to push all the elements to the hash set. Then we're going to iterate from 1 to n. And since the max element is 10 power 4, which is good enough, we can iterate it through n operations. And then we're going to check if the element is present in the set or not. If it's present in the set, we're not going to do anything. If not, we're going to check if sum plus that element is less than max sum. If it is less than max sum, we're going to increase the sum and we're going to increase the count. In the end, once the loop runs, or when the sum is greater than your max, we're going to break, because in the end it's sorted, and whatever thing you're going to get after that, whatever elements you're going to get after that, is also going to have the sum greater than max sum. So there's no point of that. Okay, so what is the time complexity of this approach? We're just iterating through this once, this array once, that is our we're iterating through the this is our n, right? Yeah, this is our n. You're iterating through the n once, this will be n. And also when you're putting all the elements in a set, you're iterating through the band array, which is also of size n, right? N. So what would be a time complexity? N plus n equals to 2n. So removing the lower order terms, we would get it as O of n. Similarly, what's the space complexity? Space complexity is nothing but the space it takes for the hash set to hold all the elements. If the band array has a n number of elements, the set also would have n number of elements. So space complexity would be n. So this will also be O of n. Okay, this is the approach. Now let's try to code it, and then let's talk about the other approach. Okay, so now let me create a hash set. Let me call it band set equals to new hash set. Okay, band set. Perfect. What I'm going to do is I'm going to iterate through the band array, and then I'm going to add band set dot add I. Done. Now what I'm going to do is I'm going to iterate from 1 to n, right? So let me take a value equals to 1. Okay, while 1 is less than or equal to n. Okay, why less than or equal to? Because it's inclusive of inclusive of n. Okay, it's 1 and n inclusive. Okay, so yeah, I'm here, and what I'll be doing is 1 is less than or equal to n. I'm gonna be checking if band set dot contains value value less than contains val, then I don't have to do anything. I can just say val plus plus. We're not this is the some people might get confused, because here we are taking value not as the index but as the element itself. Right? We're not iterating through any array. This value is the element itself, and you're incrementing the value and you're checking against the value itself. Val is not an index. Okay, next, if it does not contain, I'm gonna check if my sum, okay, I'll have to declare sum and count also. Int sum equals to 0, int count is also equals to 0. Okay, if sum plus val is less than or equal to max sum, then it's good enough. So what I'm going to do is sum plus equals to val, and then count plus equals to 1. Else what I'm going to do is okay, something that we need to check, this also will be an else condition. This entire thing will come into okay, else return count. Okay, while val is less than or equal to 1, if val plus plus, else if sum plus val is less than or equal to sum, I'm incrementing the okay, count, and also the this thing, count, else return count. No, this else would be inside this. Right, sorry. Okay, I think this is good enough. Yeah, okay. So else, can I just say return count? Okay, now val plus plus, I need to increment the value also. Okay, okay, return count, or it has processed through the entire array, and then I'm going to return count. Okay, val is given a set to 1, sum count, and val plus plus. Okay, sum plus val is less than or equal to maximum, sum plus equals to 1. Okay, yeah, let's return count, and finally I'm returning count. Sum is 0, count is 0, count plus equals to 1, plus return count. Perfect. Okay, I think it looks good. I'm adding a okay, let me run through the test cases. Perfect. Looks good. Let me submit it now. Perfect. Looks good. This runtime would be O(n). Right. Now let's talk about the other approach. Right. Now you have this band array. Okay. Let me do it. You have this band array equals to something. That is what was it? It was 1, 6, 5. Okay. Now, what are we ideally doing now? We are creating a set, and we are adding all the elements in the set, which is giving us a space complexity of O(n). Right. Can we reduce the space complexity by any chance? Yes, we can. How can we do it? Can we say that if this, see, our whole issue was searching in an array takes a time of O(n), right? Because you'll have to iterate through each and every element. Can we reduce that time from O(n) to O of log n. We can, right? If we sort this array, let's say we have sorted this 5, 6, okay, and I want to check if 5 is present or if 1 is present. I can do that easily doing binary search. Which binary search? I can set low to high, and then this would be mid. Since my 1 is less than mid, I would push my high to mid minus 1, and then do the same thing until unless I find the mid value. If the binary search gives me a true, which means that the element is present and I can ignore it. But if the binary search gives me a false, it is that element is not present and my breaking condition has been achieved. Okay, breaking condition would be low should be less than or equal to high. I can do this. Now when I do this, do I need an extra space? Actually, I don't need, right? I don't need an extra space. I can do the operation on the band array itself, which is initially, so in the band array, initially the time complexity was taking us of n for searching the elements in the band array. I'm just talking about searching the elements in the band array. Now that I have the band array sorted and I'm going to apply binary search on this, will this get reduced to O of log n? It will, right? Now it makes sense. Right, we have reduced it and we're not using any extra space. We're doing it on the same space. So my space complexity will still remain O of n after sorting and applying binary search. Perfect. Now, what about the time complexity? This is where the trade-off is happening, right? Because see, the thing is, when you're sorting it, you're applying a algorithm, merge sort, quick sort, whatever it is. You're applying the algorithm which would give you a time complexity of n of log n. Right? This will be n log n. Plus you're iterating through the elements from 1 to n. Also, you're iterating through the elements from 1 to n, which will give you time complexity of O of n. Right? Also, with this time complexity, you're checking if the element is present using binary search. That will give you log n. So can I say this to be n log n? O of n, in this iteration itself, you're checking if it's in this iteration itself, you're checking if it is present in the binary array. Band array using binary search. So you would get a time complexity of n log n. So plus n log n. Removing the lower order terms, we would get the final time complexity of n log n. O of n log n. This will be the time complexity. Now, what is the final space? This final space will be O of 1 and time complexity O will be O of n log n. So there is a trade-off happening, but ideally I would not recommend this trade-off. We can go with the approach that is mentioned, that I had performed right now, before this, because this is the optimal approach according to the constraint that is given, and this should be good. Okay. Yeah. I hope you understood the problem and I hope you understood the solution. Thank you so much for watching. Stay consistent.